Welcome to AI Paper Slop, where we summarize AI and tech papers. If you are building models, you know that they encode just, well, vast amounts of knowledge, but isolating that knowledge is incredibly hard.
Right, because of all the scale, symmetries, and, optimization artifacts baked into the physical weights.
Exactly. And today we are looking at a paper that solves this. It is called Hilbert Operator for Progressive Encoding, or HOPE, by Hossein Mobahi and Peter L. Bartlett from Google DeepMind and UC Berkeley.
Yeah, and the core insight here is that HOPE shifts network compression completely out of the discrete parameter space.
And into a continuous functional space.
Exactly. It treats entire neurons as rank 1 Hilbert-Schmidt operators.
Which is wild. And doing that enables hyperparameter-free, totally data-free pruning and merging. Plus, it introduces DEFT, which is this massive breakthrough for transfer learning.
Right. It basically solves the stability-plasticity dilemma.
Yeah, by splitting a network into a frozen universal core and a highly plastic peripheral slack.
It fundamentally changes what we consider a neural network to actually be, moving away from just looking at the literal physical hardware of the model, those massive parameter matrices in memory.
Right. It looks at the geometry of the computation itself, the actual underlying function.
Exactly.
So to really appreciate the magnitude of this shift, for anyone deploying AI, we should first establish why standard pruning methods are, fundamentally flawed.
Yeah.
Like, if I asked you to find the most important function in a massive software code base, you wouldn't just look for the longest block of text, right?
No, of course not. Judging logic by character count is absurd.
Exactly. But for years, that is essentially how we've been pruning neural networks. We judge a neuron's importance by the raw, physical magnitude of its weights.
Yeah, you look at the L1 norm of the raw weights, or maybe a batch norm scaling factor, and the heuristic is basically, well, if the number is small, the neuron must be doing less work, so it is safe to prune.
Which feels super intuitive.
It does, but it breaks down entirely when you introduce scale symmetry, which is present in almost all modern networks that use batch normalization. Those raw magnitudes are totally deceiving.
Because let us trace the math on why they are deceiving. If you take the raw input weights of a specific neuron and scale them up by some massive factor, let us call that factor lambda, the pre-activation variance of the signal spikes by lambda squared.
But the signal doesn't go straight to the activation function.
Right.
It hits the batch norm layer first. And batch normalization is designed to stabilize training by normalizing the signal, which means it divides that incoming signal by its standard deviation.
Oh, right. So since the variance went up by lambda squared, the standard deviation went up by exactly lambda.
Exactly. So the batch norm layer mathematically divides the lambda factor completely out of existence before the signal ever even reaches the ReLU activation.
Wow. So the downstream output of the neuron does not change by a single decimal point. You could multiply the weights by 1,000,000, and functionally, the neuron does the exact same amount of work.
Yeah, the physical weight looks massive, but its functional impact hasn't changed at all. Deep networks are just full of these over-parameterized many-to-one mappings.
So the raw weight magnitudes you see when you inspect a model are really just optimization artifacts.
Just historical accidents, basically, of the gradient descent path the optimizer happened to take during training. They do not correlate to true functional importance.
Which goes back to the codebase analogy. If you have a 1,000-line function that just prints empty spaces and a 10-line function that actually executes your database routing, counting the characters gives you zero insight into the logic.
Counting parameter magnitude is equally useless.
So if physical weights are deceptive, the paper argues we need to abstract away the physical matrix shape entirely and look at the continuous function. But how does HOPE actually redefine a neuron in this function space?
It transitions the entire evaluation out of discrete parameters and into a continuous Hilbert space.
Yeah.
Under the HOPE framework, a neuron is no longer just like a vector of weights sitting in a layer.
Okay, what is it then?
It is redefined holistically as an atomic unit. That unit encapsulates the incoming weights, the batch norm parameters, the nonlinear activation function, and the outgoing weights.
So you aren't separating the computation layer by layer anymore. You're evaluating the complete end-to-end signal mapping of that specific pathway.
Yes, exactly. And mathematically, OPB models this entire unit as a rank 1 Hilbert-Schmidt operator.
Okay, for the engineers listening who might not, spend their days in functional analysis, let us ground that term. What does a rank 1 Hilbert-Schmidt operator actually look like geometrically?
Well, you can visualize it as a tensor product of two distinct components. First, you have the input function. Think of this as an infinite dimensional scalar landscape.
Yeah.
And that landscape represents how the neuron reacts to every conceivable input from the data manifold.
Right.
Second, you have the output vector. This is a one-dimensional subspace that dictates the specific direction that scalar activation is projected forward into the next layer of the network. When you bind those two together, you get the rank 1 operator.
Got it. And once it is modeled this way, how do we actually measure its importance?
A neuron's capacity is measured strictly by its Hilbert-Schmidt norm. We are measuring the energy of the continuous function itself, completely independent of the parameters that generate it.
Oh, wow. So this capacity score is entirely invariant to weight resharding.
Exactly. It factors out all of those batch norm scale symmetries we just discussed. It even abstracts away the physical dimensionality of the input tensor. A neuron could have 100 incoming connections or 1,000,000. It does not matter.
The Hilbert-Schmidt norm only measures its functional impact on the data manifold.
Exactly.
Okay, the theory is beautiful, but I have a major hang-up here on the computational feasibility of this. Analyzing an infinite dimensional continuous function landscape usually requires passing huge data sets through the network to empirically match activations.
It usually does, yeah.
So if you're doing that at every single step of a compression process, aren't you introducing a massive computational bottleneck that just makes the whole framework useless for real-world application?
That empirical bottleneck is exactly what has held functional pruning back for years. Tracking empirical activations is incredibly slow, and it is highly brittle to any distribution shifts in the data you use for testing.
Right.
But the elegance of Hope is how it sidesteps the bottleneck entirely. It achieves this continuous evaluation over the data manifold without needing a single real data sample.
Wait, zero data, as in completely data-free evaluation?
Yes.
Yeah.
For any architecture utilizing batch normalization, yes. Hope extracts the empirical moving statistics, the mean, and the variance that are already stored inside the model's batch norm layers from when it was originally trained.
So it basically uses the ghost of the training data that is trapped in the weights.
That is a great way to put it, yeah.
But mean and variance are just two summary statistics. They don't give you the complex shape of the actual data set.
They don't, which is why Hope applies the maximum entropy principle. When you only know the mean and the variance of a distribution, the maximum entropy principle states that the most mathematically sound assumption you can make, the one that injects the least amount of unwarranted bias, is to construct a continuous multivariate Gaussian distribution.
Oh, so instead of feeding the model 50,000 real images of cars and trees, Hope mathematically hallucinates a statistical Gaussian approximation of what the data would look like at that exact depth in the network.
Exactly, relying purely on those stored batch norm parameters. And the beauty of using a Gaussian surrogate is that you completely eliminate the need for empirical forward passes.
Because you can just solve it mathematically.
Right. Those infinite dimensional integrals over the continuous function space, the really complex math required to calculate the Hilbert-Schmidt norm, can all be solved analytically in closed form. The framework achieves O of n runtime complexity.
Which is drastically faster than empirical methods.
Exponentially faster, yeah.
I am still hung up on the math here, though. Specifically the use of a Gaussian distribution. If you are applying this to a standard vision model like a ResNet 50, the inputs coming into a convolutional layer are post-ReLU.
Right.
And a ReLU activation means all negative values have been zeroed out. The input data is strictly non-negative. But a multivariate Gaussian distribution spans all real numbers, including negative ones. Applying a negative spanning curve to strictly positive data should completely break the approximation, shouldn't it?
You would think so. The authors actually address this directly. They call it the post-ReLU support paradox. And the resolution requires looking at what we are actually trying to integrate. We are not trying to perfectly recreate the high-dimensional, complex input distribution of the entire layer.
Okay, what are we trying to model then?
We are specifically trying to model the Hilbert inner product between two individual neurons.
So just the geometric relationship between two specific features.
Yes. That inner product mathematically reduces down to a 2D subspace, defined purely by the pre-activations of those two specific neurons. And this is where a phenomenon called the Diaconis-Friedman effect, combined with the central limit theorem, just saves the math.
Oh, let me translate that for the listener really quick. The Diaconis-Friedman effect basically proves that if you take high-dimensional data, no matter how strangely shaped heavily skewed or strictly non-negative it is, and you project it down into a very low-dimensional shadow, that projection almost always ends up looking like a standard bell curve.
Exactly. The network is completely oblivious to the complex non-negative shape of the true data manifold when viewed through such a narrow lens.
So from the perspective of any single neuron looking through its one-dimensional projection, the incoming signal already looks Gaussian.
Right. By relaxing the non-negativity constraint and using a Gaussian surrogate that spans all real numbers, HOPE maintains a tractable analytical solution while retaining a highly accurate approximation of what the neuron actually sees.
Okay, so if we can now mathematically measure a neuron's true functional power in O of n time without touching real data, the obvious next step is using that measurement to, trim the fat. How does the framework actually compress the model? It is kind of like playing a game of compression Tetris, right?
Yeah, that is a perfect analogy. HOPE unifies multiple compression actions under a single mathematical distortion metric, which they call J.
Okay.
This J represents the amount of functional damage we introduce to the model when we alter it. The simplest action is just standard pruning, deleting a neuron, and paying the cost J. But because we are operating in a functional tensor space rather than a discrete parameter space, HOPE enables a much more powerful action, merging.
Finding two redundant neurons and fusing them together.
Optimally fusing them, yes. If two neurons are highly correlated, they technically form a rank 2 subspace. HOPE calculates how to project that rank 2 pair into an optimal rank 1 parent neuron.
Wow, so it reconsolidates the distributed knowledge.
Exactly. It reclaims the capacity of the redundant child neuron and prescribes the exact new physical weights required to execute that parent function. Both pruning and merging are weighed on the exact same scale using that cost J.
That is so elegant. And the paper scales this up to macroscopic operations too, right? With block eviction. For context, in deep networks like ResNets, you have residual blocks surrounded by skip connections. Granular pruning can hollow out the internal layers of a block, but traditional methods often leave the final output layer untouched.
Right, because its dimensions have to perfectly match the skip connection for the element-wise addition at the end.
Which results in these heavily depleted zombie blocks, where most of the internal feature extraction is gone, but the heavy matrix infrastructure just stays in memory.
And it is actually worse than just being inefficient. If a block is severely hollowed out, it essentially stops extracting useful features and instead just injects an uncalibrated batch norm bias into the skip connection.
Oh, yikes.
Yeah, that rogue bias forcefully shifts the downstream feature maps out of their calibrated domain, pushing them over the zero threshold of downstream ReLUs. It causes catastrophic ReLU clipping, literally physically destroying downstream information.
So HOPE solves this by evaluating the deletion of the entire residual block, collapsing the whole pathway into a pure identity mapping. It forces the residual function to zero.
Exactly.
And because it uses the exact same continuous capacity cost J, the algorithm can fairly compare the mathematical distortion of evicting a massive residual block against the distortion of, say, pruning a single tiny feature elsewhere in the network.
Right. The continuous knapsack problem solver handles this entire process greedily. It evaluates every possible action pruning a neuron, merging a pair, evicting a block, and selects the action with the minimal distortion rate.
The distortion rate being the cost J divided by the parameter footprint, essentially asking how much mathematical damage am I causing per physical parameter saved.
Right. But a critical nuance here. The solver divides by the static parameter footprint of the initial uncompressed model.
Oh, interesting. Why static?
If the solver divided by the dynamically shrinking live footprint as the network compressed, the relative distortion rate of neighboring layers would artificially inflate. A greedy algorithm would just get trapped in a fragmented optimization state, bouncing between local minima.
Ah, I see. Keeping the parameter yield decoupled from the dynamic state keeps the global optimization theoretically sound.
Exactly.
Okay, so the empirical results back up the theory. HOPE significantly outperforms structured L1 pruning baselines on ImageNet. But for anyone listening who has tried to fine-tune a massive foundational model on proprietary data, making the model smaller is only half the battle.
Oh, absolutely.
The genuinely groundbreaking application of this framework is how it uses functional capacity to solve the stability-plasticity dilemma in transfer learning.
Yeah, catastrophic forgetting is just the bane of fine-tuning. When you take a pre-trained model and fine-tune it on a new domain, you face a brutal trade-off. Standard full fine-tuning gives the model the plasticity to learn the new task, but the gradient updates inevitably overwrite the foundational source knowledge.
Right, so the model learns how to perfectly classify your internal company documents, but it completely forgets the general syntax of the English language.
Exactly. Conversely, if you freeze the pre-trained backbone to protect that foundational knowledge, the model lacks the plasticity required to learn the new task effectively.
Which is where hope comes in, right?
Yeah.
Through a novel mechanism called dispersed elastic fine-tuning, or DEFT.
Right.
DEFT leverages the hope capacity metric to explicitly segregate the network. Since it can calculate the Hilbert-Schmidt norm for every neuron in O of n time, it identifies the high-capacity neurons carrying the heavy load of the source knowledge. It groups them into a universal core and strictly freezes them.
And then the remaining low-capacity neurons become the peripheral slack, and they are granted high plasticity to learn the target task.
It is highly structured segregation. But DEFT goes a step further with the dynamic resolution of redundancy. Let's use an analogy for this. Imagine you are renovating a house. You identify the load-bearing walls, that is your universal core. You freeze those. If you touch them, the house collapses.
Right.
But during your functional analysis, you realize you have 3 redundant load-bearing pillars standing right next to each other, doing the exact same structural work.
So DEFT identifies those highly correlated features within the frozen core and applies the hope heap merge function. It consolidates the 3 redundant load-bearing pillars into one optimal superpillar.
That consolidation protects the structural integrity of the source knowledge, but it fundamentally frees up the parameters of the other 2 pillars. You can physically vacate that parameter space and donate it to the highly plastic peripheral slack.
Right, you are taking redundant source knowledge and actively converting it into raw drywall for your new extension. You generate new learning capacity dynamically.
But wait, during fine-tuning, couldn't the chaotic gradients flowing through that new plastic slack easily bleed backward into the frozen core, causing representational drift and corrupting the load-bearing walls?
They absolutely could, which is where the paper introduces a brilliant mathematical firewall, the structural mask.
Oh, how does that work?
At initialization, before a single gradient update occurs, DEFT permanently severs the connections pointing from the upstream plastic slack neurons to the downstream frozen core neurons.
Wow, so the weights on those specific connections are hard set to 0.
Yes. Because they target a frozen core that is locked out of the optimizer, those zeroed weights receive 0 gradient updates during training. They remain 0 permanently.
Which provides a theoretical guarantee of 0 dynamic interference.
Exactly. Any chaotic drifting signal generated by the highly plastic slack subset is mathematically multiplied by 0 before it can touch the universal invariance. The new learning literally cannot pollute the foundational core.
That is incredible, and the benchmark results on this are just phenomenal. The authors tested DEFT on a severe cross-domain transfer task, moving a model trained on a specialized CFAR 100 dataset to the SVHN dataset street-level house numbers.
Right, and they evaluated performance using an H-score, which is the harmonic mean of the target accuracy and the retained source accuracy. It severely penalizes any method that suffers from catastrophic forgetting.
And the baselines collapsed exactly as expected. Standard full fine-tuning achieved an impressive target accuracy of 94.09%, but its source retention dropped to an abysmal 7.52%. It completely lobotomized the source knowledge.
Yeah, and elastic weight consolidation, or EWC, which attempts to penalize drift using empirical data passes, failed similarly. It hit 93.94% on the target, but retained only 6.74% of the source. EWC's local approximations simply shatter under a domain shift this severe.
DEFT, on the other hand, captured almost all the target accuracy of standard fine-tuning, hitting 89.79%, while retaining a staggering 52.14% of the source accuracy. It completely dominated the baselines in H-score.
Yeah, by evaluating neurons based on continuous functional operators rather than physical weights, the framework objectively separates a network's universal invariance from its malleable slack, solving the stability-plasticity dilemma purely mathematically without needing a single source data sample.
The broader implications of transitioning into functional evaluation are just massive, particularly when you consider concepts like the Platonic representation hypothesis, which the authors briefly note.
Yeah, that is a huge point.
For the listener, the Platonic representation hypothesis suggests that diverse neural networks, regardless of their underlying architecture or training data, are all converging on shared statistical models of reality. Their physical weights might look completely different, like different shadows on a cave wall, but the underlying functions are aligning.
If the OPP framework proves that we can accurately map, isolate, and manipulate these models based purely on their continuous functional operators in a shared Hilbert space, it raises a really profound question. Could frameworks built on these functional operators eventually allow us to directly translate learned concepts between completely different neural architectures, moving knowledge seamlessly across domains without ever needing a single piece of training data?